Hey, welcome back to Advanced Mechanics. Today we'll be looking at another Lagrangian example. In this case, it's going to be a box sliding down a moving incline. So here we have a box of small m, and it's going to slide down the incline. And as it's sliding down the incline itself, which is connected to the surface right here, I guess I shouldn't say connected, but it's allowed to move freely. There's no friction between the surface and this. And we don't know if the incline's actually moving with the initial speed or not, but it could. So that's what we want to know. We want to know the equations of motion of this object when the bigger object can also move as well. So to do that, we're going to have to write down our, kinetic and potential energies. So let's start with the kinetic energy. And the total kinetic energy is going to be the energy of this object and the energy of this object. So the energy of the big object is pretty straightforward. It's just 1/2 big M x dot squared, where x dot is the velocity in the generalized coordinate system. And then we're going to add to that the energy of the smaller object. And now the smaller object has two different energies. It has the energy going down the incline, but it also has the energy of this whole thing being moved that way, or whichever way. So we're going to have to write that as 1/2 m parentheses x dot plus, let's see here. Oh, and I even named these. So let's call this one x1 here, so that way I don't get confused between the two. And so if that one's x1, this one is also going to be x1, and then this is going to be x2. So plus x2 dot squared. And so remember, these two aren't in the same direction, so we're going to have to take the dot product of this when we square it. So let's just do that, and we're going to end up with 1/2 big M x1 dot squared plus 1/2 m. Now we have to square this, so it's going to become x1 dot squared plus x2 dot squared plus, when you take the dot product of these two, it'll be x1 dot x2 dot cosine of theta. And I'm forgetting a 2 here because you have two of these. So where can I fit that 2? I'll just do this. Times 2. Okay, so that's what we end up for the kinetic energy, and later I'll bring the 2 into the front. How about the potential energy? The potential energy, which is U, well, I've defined the minimum potential to be at this height, and it's going down, so we're going to have a negative value for the potential, and we could write that as negative. How far is this going to go down? It'll be x2 times sine of theta, because this angle right here is theta. So we'll end up with m little, or lowercase m times g, times x2 sine of theta. And that's the only potential energy that we have in our system. So now that we have these two, we can write down our Lagrangian equation, and that'll equal, where do I want to write that? I guess I could write it up here. L, which is equal to T minus U, is equal to 1/2 big M, or capital M, x1 dot squared plus 1/2 little m parentheses x1 dot squared plus x2 dot squared plus 2 x1 dot x2 dot cosine of theta. And here theta is a constant. This incline's not going to change its angle. So let's just remember that much as well. Okay, so, oh, and I'm forgetting this part right here. So it'll be the minus this value right here. So it'll be plus little m g x2 sine of theta. and that is our Lagrangian. So now we're going to have to find the equations of motion for x1 and x2. Which one should we start with? Let's start with x1. So writing down our Lagrangian Euler equation, we have the partial of the Lagrangian with respect to x dot, and we take the time derivative of that, d dt, and that's going to equal the partial of the Lagrangian of x. So this is going to be for both x1 and x2. Let's do it for x1 first. So I'll call this x1 and x1 as well. Okay, so let's start with this side right here. What is this term going to equal? If we take the partial of the Lagrangian with respect to x1, what do we get? Well, there is no x1. This is an x1 dot, so that doesn't matter. Nothing here, nothing here, nothing here. There is no just regular x1. So the partial derivative, everything is a constant with respect to just x1 by itself. So that's going to equal 0. Okay, good. How about this part right here? The partial of the Lagrangian x1 dot first, and then we'll take the time derivative after that. So that's going to equal, let's see here. Okay, there's an x1 here, so we bring the 2 to the front. It's going to become big M, or capital M, x1 dot, all right, plus there's an x1 here, so we can bring the 2 to the front, and it's going to become little m, x1 dot. This is a constant with respect to this variable here, so that doesn't matter. Over here, all right, we have an x1 here. This is going to become 1, and then you multiply this, 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 and then these two together. So the 2 and the 1/2 will cancel each other out, and we'll have plus m lowercase x2 dot cosine theta. So then we go on to this term right here, and it looks like there is nothing there for x1. So that's what the partial is with respect to x1 dot. And then we can take the time derivative of this term here. So d over dt of the partial Lagrangian with respect to x1 prime. Doing that, this becomes m x1 double dot, good. The next one would be plus lowercase m1 x double dot, great, plus theta is a constant, so it's going to be m theta times this term, which is going to be m x2 double dot cosine theta. And all of this term right here has to equal 0. So we have our first equation for the Lagrangian. And can we do something? Let's actually clean it up a little bit. Let's separate the x1s and the x2s from each other. So we'll end up with x1 double dot parentheses big M plus little m is equal to negative m x2 double dot cosine of theta. Okay, and that will be our first equation. We're going to have to do a little bit more because you have two different accelerations in this equation. So when we do the Euler-Lagrange equation again for x2, we should see, one of these things cancel out. So let's do that. I'll do that. Where can I do that? I'll do it right here on the bottom. Hopefully you can still see most of the Lagrangian there. So let's start with dl over the partial x2 without the dot there. So let's look for x2s in our Lagrangian equation without the dot. Okay, this is a constant, this is a constant, this is a constant, this is a constant. Only this thing survives, and the derivative of this just becomes 1. So you're left with mg sine of theta. So, okay, that's not bad. We've got mg sine of theta. Great. Now let's do the second part, which is dl over dx2 dot. And let's find the partial derivative of that. Let's go to our Lagrangian. This is a constant. The first term is a constant. Oh, the second term, we can bring the 2 to the front. It's going to cancel out, and we get mx2 dot. So mx2 dot, great. Over here, oh, we got this one. This becomes a 1. The 2 and the 1/2 will cancel each other out. So we get mx1 dot cosine theta. So mx1 dot cosine theta. And is there anything else we have? So that we took care of that. And this one doesn't have the x2 dot, so it's a constant. So that's what we're starting with here. All right. And then what can we do from there? We can, let me just make sure I have everything correct. That's fine. And yeah, it looks good so far. It's easy to make mistakes here, so I just have to check my work all the time. Now let's take the time derivative, d dt, of the Lagrangian, dx2 dot, and that's this right here. So this first term becomes mx2 double dot, great, plus this term right here, which is only this thing's a constant, so it'll become mx1 double dot cosine of theta. So this is equal to this. Let's put that together because the Euler-Lagrange says that this term is equal to that term, right? This term is equal to that term. So let's set them equal to each other. We get mg sine theta is equal to, on the other side, we have m parentheses x2 double dot plus x1 double dot cosine of theta. And we can see that the m's will cancel out. And if we separate this, how do I want to separate it? We can solve for x1, I guess. So if we get x1 by itself, it's going to equal, actually, I'll leave that for now, and then we'll work it out on the other side. So we'll just leave this as g sine of theta is equal to x2 double dot plus x1 double dot cosine of theta. And that is our second equation. So we have two equations with two unknowns. We're going to solve for x1 and as well as x2 on the next page. Okay, so here we are. We have our two equations. I just brought this g term to the other side. This was equation 1, this was equation 2, and now we just have to solve. So what I'll do, we could do a couple of different ways of solving this. We can bring these two terms to the other side and then substitute for x2. Whichever way you want to do it is up to you. Let's see, I'll take this term and then divide it to the other side and then substitute it into there. So what we'll end up with is x double dot squared plus, I'm going to change x1 to this value right here. So it'll be plus negative x2 double dot m cosine theta divided by big M plus little m. So that's taking this term right here, placing it into there. And then we also have the cosine theta minus g sine of theta. And all of that has to equal 0. So from here, we can factor out the x2. So we get x double dot squared, the acceleration, I guess, parentheses 1, because there's 1 here and then there's 1 there, 1 minus, plus minus becomes minus sign, m cosine squared theta, cosine goes into here, yeah, that works, cosine squared theta, and we have big M plus little m equals g sine of theta. All right, so I brought that term to the other side again. And then if we want to solve for x2 double prime, we just divide this term to the other side. So we get that x2 double prime is equal to g sine of theta divided by parentheses 1 minus lowercase m cosine squared theta divided by big M plus little m. And can we make this look a little bit nicer? I think we can. What I could do is multiply the top and the bottom by lowercase m. So I'm going to take this equation and multiply the top by big M lowercase m and the bottom by big M lowercase m. And when we do that, forgot a parentheses there, this thing gets distributed into here, that'll cancel out, and then it gets distributed into here. So we end up with x double dot 2 is equal to g big M plus little m sine of theta divided by the first term, which is going to be big M plus little m minus m cosine squared theta. And that is going to be our first equation. Here's what's really cool about this equation right here. All of these are constants. M is a constant, theta is a constant, g is a constant. So the acceleration along the x direction, or the x2 direction, is going to be a constant value. So what that implies is, we could say that x2 double dot is equal to, we'd say, a2, which is a constant. And so if you take the integral of these with respect to time, you will get your basic kinematic equations that you learn in regular physics. So we could use the equation Vf equals V naught plus, in this case, A2 times T. We could use the equation delta X is equal to V naught T plus 1/2 A2 T squared, and we could use the equation Vf final squared equals V naught initial squared plus 2 A2 delta X. So all of these equations work, and the X's that we're talking about are X2s. So I should call that X2, and there's an X2 there. So that's what we end up with that right there. Awesome. Let's do the other one, x1, and see if that's a constant as well. Spoiler alert, it should be. So let's see here. I need to straighten this out a little bit. And let's do x1 now. So how am I going to do x1? We said that x1 double dot was equal to negative x2 m cosine of theta divided by big M plus little m. All right, we had said that. And so what we're going to do is substitute for a x2. So x2 was equal to this value right here. I'm going to do it using this instead of this one right here because it's just easier to work with. Oh, and this should be x2 double dot, right? We solve for x1, and it's going to equal that term. And all this is in parentheses. And now what I'm going to do is I'm going to take this value, without the m1s and substitute it in for x2, and let's see what happens. So x1 double prime is going to equal negative parentheses big G sine of theta divided by 1 minus m cosine squared theta divided by big M plus little m. And that should be it. And we multiply that by m cosine of theta. So there's that. And then we have to divide the whole thing by big M plus little m. So what is this going to become, this nightmare of a thing? Well, all of this term right here can be brought to the denominator, so that's kind of nice. And then we're left with negative g sine theta m cosine theta. So we'll write that as negative g times lowercase m sine theta cosine theta. And in the denominator, we have 1 minus m cosine squared theta divided by big M plus lowercase m multiplied by this term right here, which is big M plus lowercase m. And this is nice. You could distribute this into here and here, and we will get that x, is there a way we could clean this up a little bit? Nah, I think that should be fine. So x double dot 1 is going to equal negative g lowercase m sine theta cosine theta divided by big M plus lowercase m minus m cosine squared theta. Looks similar. This one has to do with a negative sign. So it looks like one is going to be accelerating one way, the other thing's going to be accelerating the opposite way. Makes sense. When a thing slides down, the incline gets pushed that way and the other object will get pushed the other way. So that sort of makes sense. And everything else looks pretty nice. This is all a constant here, so great. This is our second equation of motion. And again, it's constant, so we could do the same things here except for A2, or sorry, A1, and then we can figure out what the position and the velocity terms will be for an object going down an incline with the incline moving. Okay, so that's it for this one. I'll see you in the next lesson. Adios.